Let's try one more problem. Consider this reaction: CO plus Cl2 will yield COCl plus Cl. Now, we have 2 moles of gaseous CO and 3 moles of gaseous Cl2 introduced into an evacuated 4-liter flask, and the reaction is allowed to come to equilibrium. Kc for the system at the reaction temperature is 0.52. Calculate the concentrations of the reactants and products at equilibrium. So go ahead and pause the slide and work this out. Determine whether you will need to use a quadratic equation or not. You can use the 1% rule to help guide you in that, and I'll see you after you're finished. Welcome back. Let's see how you did. First thing is to set up the ice chart, and you can see here, put the values in. The starting concentrations of carbon monoxide and chlorine. You just take the number of moles divided by the volume of the flask, which was 4 liters. So you have 0.50 moles per liter of carbon monoxide and 0.75 moles per liter of chlorine. The stoichiometric coefficients for each of these are 1, which is convenient for us. So they will change by the amount of minus X for the carbon monoxide and chlorine. The starting concentrations for COCl and Cl are 0 and 0, and so these will change by a plus X value for each of those. So at equilibrium, you'll have 0.50 moles per liter minus X for the CO, 0.75 moles per liter divided by X for the Cl2, and then X and X for the COCl and the Cl. I'm going to go ahead and show you the 1% rule calculation, and you'll see that the value of Kc divided by the initial moles per liter of the CO times 100 comes out to be 104%. So the 1% rule here does not allow 0.50 minus X to be essentially equal to 0.50. So a quadratic must be used here to solve for X. As we work through the progression of solving for X here, because we will be using a quadratic, there's going to be a lot of information on the slide, and I don't want to have to read that. I think probably listening to it may be more confusing than just looking at it. So feel free to pause these slides at any time and copy down what you need to copy down. Hopefully your work will match mine and you already have it, but pause at any time and work through that. And the first thing here, once I have the ice chart, is I go ahead and write the equilibrium constant expression. So I have my 0.52 is equal to the products of the concentration of COCl times the concentration of Cl on top, divided by the products of the concentrations of CO times Cl2 on the bottom. Using my values from the ice chart, I then have X times X over 0.5 minus X times 0.75 minus X. This is not a situation where you can use the concept of the perfect square to simplify. So we have to gut through that concentration, or gut through the algebraic manipulation to solve for X. So what you see next is simplification of both sides, X squared on top, and then multiplying through the quantities on the bottom. So you end up with X squared on top divided by X squared minus 1.25x plus 0.375, all that quantity being equal to 0.52. As we continue through this progression, I multiply both sides of the equation by what's on the bottom of the right side, x squared minus 1.25x plus 0.375, so that I can eliminate it from the right-hand side of the equation and begin my simplification process. Once we get the x squared minus 1.25x plus 0.375 quantity on the left side of the equation, we multiply it by the 0.52, and so we end up with 0.52x squared minus 0.65x plus 0.195 is then equal to x squared. Going to subtract the quantity from the left side of the equation from both sides of the equation so that I can get this set up as in a quadratic form. So when I subtract it from the left side, obviously I'll have 0 is equal to, on the right side, 1x squared minus 0.52x squared plus 0.65x minus 0.195. And that 1x squared minus 0.52x squared leaves us with 0 being equal to 0.48x squared plus 0.65x minus 0.195. I can then use my quadratic to solve, so my negative b plus or minus the square root of the quantity of b squared minus 4ac divided by 2a. And you can see I've plugged the numbers in so that you can see the final outworking of that base quadratic form. Continuing to solve through the quadratic, and again, if your instructor allows you to use a TI-83 graphing calculator that has a program for solving quadratic equations, it simplifies this and saves you a lot of time. If not, you'll have to crunch through this the way that I show here, but in the end, as you go to solve for x, as we continue to simplify, you'll have negative 0.65 plus or minus 0.8926 divided by 0.96. Continuing to solve for the two quadratic roots of x here. The first one, the negative 0.65 plus 0.8926 divided by 0.96 gives us plus 0.25 moles per liter. X2 would be negative 0.65 minus 0.8926 divided by 0.96, which gives us negative 1.6 moles per liter. The X2 value, negative 1.6 moles per liter, cannot be true. For one, if you look at your ice chart, you don't have high enough starting values to have 1.6 mole per liter change on any of those. So your positive value here of 0.25 moles per liter is correct. Since we know that the value of x is 0.25 moles per liter, it's the only possible value that will work and make coherent sense with this. We then plug it back into our ice chart for our equilibrium value. So we have 0.50 minus 0.25 moles per liter gives us an equilibrium concentration of 0.25 moles per liter for our CO. For our Cl2, 0.75 minus 0.25 moles per liter gives us an equilibrium concentration of 0.50 moles per liter for the Cl2. For our COCl, our concentration is just plus X, which is plus 0.25 moles per liter or 0.25 moles per liter, and the same for our Cl. It would also be 0.25 moles per liter. We are having such a wonderful time together. Let's do one more problem. Here we have ammonia gas decomposing into nitrogen gas and hydrogen gas, and this is an equilibrium reaction. So at equilibrium, a 2-liter flask contains the following partial pressures of reactants and products. We have 0.75 atmospheres of ammonia gas, which is NH3, 1.20 atmospheres of nitrogen gas, N2, and 3.60 atmospheres of H2. Our goal is to calculate Kp and Kc for the reaction, which occurs at 25 degrees Celsius, and Kc for the reverse reaction. So at this point, go ahead and pause the podcast and work the problem, and I'll see you back here in a few minutes. Welcome back. Let's see how you did. Now, in this one, because we're given the pressures in atmosphere, we're going to set up and solve for Kp first. So Kp will equal the pressure of nitrogen times the pressure of hydrogen cubed divided by the square of the pressure of NH3 or ammonia. So once I've done that, I can substitute in my pressure values. On top, we'll have 1.20 atmospheres times 3.60 atmospheres cubed divided by 0.75 atmospheres squared. And as we calculate that, we get a Kp of 99.5. How'd you do? Let's see how you did in terms of converting Kp to Kc. We use the relationship that Kp is equal to Kc times the product of RT raised to the power of delta N. Delta N, in this case, there are 4 moles of gaseous products, and there are 2 moles of gaseous reactants using the stoichiometric coefficients in the balanced equation. So we take 4 minus 2 is equal to 2. Our R value is the universal gas constant, 0.082 liters times atmospheres over a mole times a Kelvin. And our temperature is given to us in Celsius, 25 degrees Celsius, so we have to convert that to Kelvin in order to use this. So 25 degrees Celsius plus 273 gives us a value of 298 Kelvin. Solving for Kc, we have that equal to Kp divided by the product of RT raised to delta N. So on top we have Kp, which is 99.5, divided by the quantity 0.082 liters times atmospheres over mole times Kelvin times 298 Kelvin squared. And the value for Kc that we get is 0.17. So when we convert Kp to Kc for this reaction, we get 0.17. And then we want to find Kc for the reverse reaction, so all we do is take Kc for the reverse is equal to the inverse of the Kc for the forward reaction, or 1 over Kc forward. So this would equal 1 over 0.17, which is equal to 5.9. Hopefully you did well with that. If you had problems with these your turn problems, I would recommend that you stop the podcast, go back. You can slide back to where you need to go and rework them, and that will be helpful to you. And if you need more help, certainly find a fellow student who's doing well with this. They'd be glad to help you, or your instructor. This is the end of part 1-8 of the Equilibrium video podcast series here at Ontario High School. I want to leave you with a quote from Mark Halperin. The shelf was filled with books that were hard to read, that could devastate and remake one's soul, and that, when they were finished, had a kick like a mule. So I wish you well. There's one more part after this, and then you're at the end. So good luck.